Right, on we go then. So we talk about silicon now, and you don't know loads about silicon, do you? You're not taught loads about silicon. You have to work some stuff out here from the information given, and that's a normal thing to have to do, and that scares some people, but don't worry if it comes to it in the exam. You can use the knowledge you have to answer all the questions, in theory at least. Right, so reactivity series, which you're familiar with, mostly metals, but sometimes we write carbon and hydrogen in there, or silicon in there. We can extract silicon from silicon dioxide by using carbon, and that shows you that carbon must be more reactive than silicon, because more reactive elements displace less reactive elements from compounds, and that was answered really well actually. So silicon less reactive than carbon. Be clear in your answers actually, please. So be clear that it's less reactive than carbon. Don't just say it's less reactive. Be really clear about what you're talking about. Otherwise you could be talking about hydrogen or something else, couldn't you? And then the reason why we know that is because carbon displaces silicon from silicon dioxide. That's that one, 2 marks, tick tick. Okay, well done on that, largely done well. Aluminium also reduces silicon dioxide. This is a reduction, isn't it? Because the carbon is taking oxygen away, or if you like, the carbon is gaining an oxygen is the way we describe it for GCSE. So we'll leave it there. Okay, and the silicon's losing an oxygen. Aluminium can do the same, so aluminium would form aluminium oxide, and the silicon would be reduced, right? I don't really know what's telling you all that stuff, but you simply have to explain this. So why is aluminium more expensive than carbon? And this is just some knowledge that you have to draw on from your teaching, right? So aluminium is more expensive because it must be extracted using electrolysis. And the reason why is that it's more reactive than carbon. So you can't use the normal process of smelting that you can use, like up here with silicon dioxide, or with or true smelting, which is reduction of iron oxide. You have to use electrolysis. Now, some of you went on to explain why that is expensive by talking about the fact you have to dissolve in molten cryolite, and you have to heat it up, and then you have to use electricity to do the electrolysis. What the mark scheme insisted you had in there for the mark was that lots of energy required, so much more energy required, so more energy is needed, and that's what the mark was for. And that energy is needed for the electricity. It's also needed for the melting of the cryolite with the aluminium oxide, right? So that's what the mark was for. This one, most of you got this reasonably well. They recognised that silicon, magnesium oxide are both solids. So you can do this reaction, the same reaction with magnesium and silicon dioxide to get silicon, but they're quite difficult to sort and separate afterwards because they're both solids. Now, if one thing's a liquid metal, let's say, and one thing's a solid, you can separate really easily. But if they're both solids, very hard. Can you think of any processes to separate two solids apart from using a magnet? Magnets won't work on this, will they? So both solids is the mark. So then the calculation was done largely pretty well, unlike one of the other calculations later, but I'll just go through that now. So you're given the equation, so I'm just going to write this out again as the way that we've all been taught, I think, in year 11. So you've got magnesium reacting with silicon dioxide to give silicon and 2MgO, right? So with any calculation, work out the number of moles, and if you've got masses given to you, you can work out the moles by using the formula masses. In other words, using these numbers here as well. Okay, using moles equals mass in grams divided by the formula mass, mR. Right, that's the equation you're going to use. You don't always work out moles using this approach. You can work out moles from gases which we'll talk about later on, or you can work out moles from volumes of solution by using the volume and the concentration. Here we're using the MR. So it's worth always writing the molar ratio, showing that silicon dioxide and magnesium are reacting in a 2-to-1 ratio to give silicon and magnesium oxide, and then just fill in what you know. Right, so you know the mass. Please write mass in grams, and you've got a mark actually for converting the kilograms into grams, because if you're going to work out the number of moles, you need to work out the mass in grams first. You've got a mark for that, and you've got a mark for working out the formula mass. Now, when working out the formula mass, I've always taught people to put a box around the thing you want the formula mass for, so you don't make the mistake of multiplying by 2. A few of you totted up this wrong. So 1 silicon is 28, plus 16 plus 16 is 60. Okay, so 60 there. And then you work out N, the units for which, so moles, N is the amount in moles. To work out the amount in moles, you do mass over MR, so 1,200 divided by 60, and that comes to 20. Then you use the ratios to work out how many moles of magnesium were required, which is what we've been asked to do. So it's a 2-to-1 ratio, so you times that by 2, and you've got a mark for working out that 40 moles are required. And if you got a wrong answer somewhere, you should have got a mark for multiplying the number of moles by 2. And you had to work out the mass of the magnesium. Remember, the mass in grams, it's just a rearrangement of the equation above. It's equal to the MR times the number of moles, which is 24 times 40, which is equal to 960. I'm going to fill it in the table there in grams. I'm going to write it down here as well, 960. That got 5 marks. And lots of you did that very well, so well done. You saw all that. Question 7.5 was a dot and cross diagram. I don't much like the way they've drawn it in the mark scheme, but you can work this out. So this is not one you've seen in class. I've never taught this in class myself before, but you can work it out because you should see that silicon is in group 4. If silicon's in group 4, it's got 4 electrons in its outer shell, which means it makes 4 bonds, just like carbon above it. You can say it's got a valency of 4 is another way of putting it. Hydrogen, you know, can only accept 1 more electron in its outer shell, which means it can only make 1 bond. So quite often good practice, if you're struggling with these, to draw the kind of stick diagram to start with, which would look something like this. And you just quickly check that silicons have each made 4 bonds, hydrogens have each made 1 bond. That's what it would look like, and each line is representing a pair of electrons. So you can then draw the dots and crosses. They don't care at GCSE whether you draw dots and crosses, or dots, or just crosses. I don't mind, as long as you draw on a dot and cross and it goes in the overlapping area, and that would get the mark there. So this question was a stinker. Very good, very tough question that lots of you struggle with. This is more or less, year 12 chemistry, I would say. So I'll go through this one with you. I think this was a juicy challenge, right? So here we're doing gas calculations. Unusually with calculations, you don't need to work out the number of moles in a gas calculation, because every gas at room temperature and pressure has the same volume. It has a volume, as it happens, of 24,000. 1 mole has a volume of 24,000 centimeters cubed, or 24.0 decimeters cubed, which is the same as a litre, isn't it? Okay, so we don't actually need to use these numbers. We can use the ratios simply in these to work out the answer. All right, let's have a little go then. So again, it's just good practice to write out the equation so you can just see what's going on. It gives you a moment to think about it, and we can set it out really clearly, hopefully, beneath. The first thing I point out to you that silicon dioxide is a solid, so that's not going to be part of your volume as a product, and some of you didn't realise that, unfortunately, which lost you some marks. And you fill in, you've got your table, you fill in what you know, starting with the molar ratios, as always. So the molar ratio is 2 to 7 to 4. Not that that's useful because it's a solid, and water is a gas, so that is interesting and useful there. You're told you've got 30 centimeters cubed of the silane, so Si2 H6, 30. We'll write the units here. Right, and what else are you told? You're told you've got an excess of oxygen, 150 centimeters cubed. Right, now this stuff and this stuff react in a 2 to 7 ratio, or if you prefer, a 1 to 3.5 ratio. So really for this one you have to recognise which one is the limiting reactant first, but you're told that anyway, so you're told that's in excess, so I can make a little note of that. It's an excess, and this is limiting here. So all of this is going to get used up, but not all of this is going to get used up. You're going to have some oxygen left over there, you're told that, and that has to be included in your final amount. So let's think. So all 30 centimeters cubed of the Si2H6 are going to get used. But how many centimeters cubed of oxygen are going to be used? Well, there's a 2 to 7 ratio, so you times 30 by 3.5, and you get 105 centimeters cubed. So I'm just going to write underneath used, so, or change we sometimes write. So 30 are used up of that stuff, but 95 of that stuff are used, so minus 95, or change is perhaps a nicer way of putting it. So 35 there been used, 30 been used up there, 95. And remaining, we've got 0 centimeters cubed of that stuff. We've got 150 take away 95, which is what was that, 45, isn't it? What have I done wrong? I've done something wrong. It's not 95, it's 105. Sorry. And that leaves you with 45. Just double check that quickly. Yeah, 3.5 times. Sorry. Okay, so you've got 45 of, just to set it again, 30 of this is used up. And so 3.5 times 30 is 105, so 105 of this is used up. So we're left with 45 centimeters cubed of oxygen at the end. Right, so how much of this is produced is irrelevant because it's a solid. Solids don't have a volume, in comparison to gases at least. And the ratio between this stuff and the water is 1 to 3, 2 to 6. So we can times this by 3, and so we must make 90 centimeters cubed of that stuff. And lots of you worked that out, so well done. So we start with 0 and we end up with 90. So the total volume must be whatever was left of the oxygen, add to whatever you've produced of the water, which is 135 centimeters cubed. Extremely well done if you worked that out. I think that was tough, and even I mangled it there, so don't worry if you did. I think that's a good place to stop.